Okay, we're live on YouTube as well. So welcome to this final class for the advanced topics in reinforcement learning. And yeah, so we'll be talking today about distributed reinforcement learning and parallel training. And actually, I hope today to be a bit shorter than at times. We don't have a lot of videos, so I think we can be aim at less than 1 hour possibly. Okay, so let me share the screen. Okay, if you can see it, I guess so. We can enter in presentation mode and start. Okay, so there are several architectures for doing reinforcement learning in a distributed fashion. But first, let me talk about why you would want to do distributed reinforcement learning. So this is probably quite obvious, but as many problems can be very complex, then you want to be able to collect a lot of data to train your agent. And in order to do that, a very efficient way to do it is to parallelize your computation in the policy execution side of things, so that you can basically sample more transitions from the environment in parallel and then use them for training. Of course, I have been talking about data collection, but another point could be I also want to parallelize the training phase of things. And then this is another reason for distributed reinforcement learning. Although most of the scenarios that we'll cover have multiple actors that collect data to be then used and exploited by the trainer, because this is the most common scenario that you have. So this can happen on in a really distributed fashion when you have several machines on which you run your actors. These are typically called rollout workers. And then you have a trainer machine that gathers the data and then returns the information to the actors regarding the policy. This can happen in different ways, but we'll see now how this happens. This is the truly distributed approach. Then you can have also locally distributed among different processors, where you on which you have on each processor an actor, and then you exploit shared memory in order to communicate information between the actors and the learner. Okay, so these are the reasons to do this. Each architecture has an implication both at inference and at training. So inference can be distributed and or centralized, even if you are working with distributed actors. So when you have distributed inference, you can have several architectures where either you have each actor that estimates the gradient and then passes the gradient information to a global policy network or trainer, which aggregates them and updates the weights and then returns a snapshot of the network itself. This is the first figure that I'm talking about, the top right one. Then the bottom right one describes a slightly different situation where you have each actor that is just collecting experiences and sampling transitions from the environment and then returning again. The learner performs all its updates. Notice that it's the only one that computes gradients in this case. And then it returns like in the previous case, a snapshot of the policy and the value network. Yeah, so you can see an animation of this in the left figure, where internally to each actor we have a typical reinforcement learning loop where the environment returns an observation to the model returns an action which gets stored, and then this gets communicated to, the trajectory gets communicated to the learner. And at the same time, the action goes in the environment to return a new observation. And this happens basically the same way for each actor. Then in the learner, the data that are stored in this queue are sampled in batches and the model is optimized. And every once in a while, the agent returns some parameters to the different actors. So this is where the distributed side of things is only on the actor. So that's why it's called distributed inference. So the distributed part is only on the actors. So there is no distributed training, right? It's distributed data collection, so distributed inference, but not distributed training. Another scenario is where you not only have centralized training, like in this case where the only training is happening in the learner, but you can also have centralized inference. Right, in this case, you have several actors that have basically an environment, and this environment returns an observation that gets passed directly to the learner. All the observations from each actor get collected into a batch, and they are passed through the model. The model returns a batch of actions, which are then splitted to be delivered to the correct actor. So this is a centralized inference approach. The distribution can be not only at inference, but also at training. So the case that we have seen so far is the one where we have a single learner. But another common approach is when you have multiple learners that are synchronous. So they exchange gradients in a synchronous fashion. They communicate in a synchronous fashion. And so each of them then has the same information. They return the parameters to the actors. Of course, why do you want to do distributed training? Because at this, in this case, the computation of gradients is distributed. So you are basically reducing the amount of time that you need in order to perform a single update. But anyway, then they communicate each other the gradients that each of them has computed, and the update is performed in a synchronous way with the same values. Okay, so now that we have a clear idea what they are, the architectures, we can focus a bit more on the approaches that implement these different architectures that we have just described. The first algorithm I would like to talk about is A3C, which is asynchronous deep reinforcement learning, where we have this decentralized inference. But in this case, it's the first architecture that we described, this one, where each actor here computes the gradients. Then these gradients are accumulated and updated all together, and there is this parameter server that returns the correct parameters to each actor. So the idea here is that you have an actor and a gradient estimator for each distributed machine, and then we scale up the training with multiple CPUs because we have more data collection, so we can have shorter training times related to the data collection side of things. And also the training is typically more stable because the different actors are in different steps of the in different parts of the observation space of the environment, meaning that in this case, you have more IID data, more independent and identically distributed data. So you're decorrelating your data, which is one of the issues of the reinforcement learning training, as we discussed some time ago. So this is quite an alternative to replay buffer, because in this case, in fact, we are doing on policy training. So this is not off policy, but it is on policy. And of course, the advantage of doing such a thing is that it's less memory intensive, but of course, you can do this only if you have distributed machines and you want to do on policy training. We'll see that this constraint will get rid of it anyway with the next algorithms that we will look at. So if we want to look at the details, here we have an environment. So we have a single policy network, which is the central machine to which each worker then communicates. Each worker has a copy of this global network that is used in order to compute the parameters given the environment observation and actions that have been collected during some trajectories, and then they communicate the gradient updates. And we can check this happening also in the pseudocode, where again, each actor internally is communicating, collecting transitions of state, actions, reward, and next states. And then when the state is terminal, it uses bootstrapping, otherwise it doesn't. It computes the returns, and then it uses the returns in order to compute the gradients, both for the policy and the value. Note that here you have a global network where the weights of the policy and the value network are shared. So this means that we are computing a common representation for so a common set of features for the policy and the value network then to use. This is just what it means to have a shared weight network with different heads, one for the policy, one for the value function. And then we perform an asynchronous update when we send the data to the global network. The network updates based on this single accumulated gradient that this worker sent, and when it receives all the other, it does the same thing. And in exchange for this, it returns the parameters of the network to be used by the worker. Okay. And this is this step: synchronize thread-specific parameters from this global network. And as I said, you can do this with several threads on a single machine, with several processes on a single machine, and so on and so forth, or otherwise in a purely distributed fashion with a machine which is completely independent from the others, where they communicate by means of some remote calls. Okay, then we can compare some of the results that we have by increasing the number of threads, where if we have a single thread, it means that we are performing basically advantage actor critic, which is the algorithm that is made asynchronous and distributed by this A3C. And you can notice that by increasing the number of threads, the training score goes up and up with the same amount of time, which is what we would expect. So they also compare against other algorithms. So you can notice that A3C compared to DQN returns much better result in a reduced amount of time. And again, this is what you would expect, right? Because the data collection side of things is much faster. From A3C, let me push to this slide where we have a timeline here. So before there was DQN, which was the first deep neural network reinforcement learning algorithm. Then Gorilla was a first approach attempting to parallelize things, but A3C was the real first algorithm that made a difference from this side of things. Then there was Ape X, which we'll discuss, and Impala. Now, the order of these things in our discussion will be slightly different because of the discussion that will be following. But so Impala, just to put things in time, came 2 years after A3C. So going back to Impala, for which you find the official code here, is an algorithm that basically changes the architecture of A3C in a quite simple way in some senses. So the here the actors only generate trajectories. So it's the second architecture that we have seen, this one. They only generate trajectories. They are stored then into a queue, which the learner dequeues to collect batches of trajectories and perform the parameter updates. So this is the case where before in A3C we're getting computed gradient information. Here we're getting just the transitions. Okay, now this brings an issue, because if you decouple the gradient computation to the actual policy state, the actual policy, then you need to do off-policy learning. So you need to change the way you're doing training, because the actor parameters can be updated at different times, so they can have different versions of the central policy that we have. So they can be much behind what is the current state of the policy. So how can we solve this? So as I mentioned, first of all, we need to do off-policy learning, and we specifically in Impala, they come up with an off-policy advantage actor critic formulation that attempts to compensate for this issue that we just described, where the trajectories are collected by means of actors that are old versions. So it's not anymore the same policy that we're not training anymore the same policy that is generating the data, but the policy is effective in an effective way. Another policy, a previous policy, a past policy. So this is why we need to do off policy, and they solve this problem mostly by using importance sampling. So they compute these weights that are injected in these V-trace targets. So the V here is the target. This is the this is the current version of the value network, and then this is the way you would compute the gradient. Except that this is the standard formula. Now the target is computed in a slightly different way, where we have these important sampling weights C that are defined in this way. So I mean, it's just using of policy learning with important sampling on an advantage actor critic formulation, and yeah. The idea is simple, but it works pretty well, because if we go then to compare Impala against A3C, we notice that the performance on several tasks returned by Impala is much better. And yeah, so this is one side of things. The other point that I wanted to make is that Impala not only works in a distributed inference setting, but also in a distributed training setting, where the learners, however, are, as I mentioned before, perform synchronous updates. Okay, so here you notice that there is the single machine comparison and the distributed comparison with different settings, where A3C has 32 workers, and IMPALA has 48 actors and other parameters that are changing anyway. And you see what this is the amount of frames that are collected per second, and this is the same thing for the same comparison that we get in the distributed setting. Another algorithm that performs off policy in this case, actor critic updates, is distributional DDPG, or another version of it is distributed DDPG. So this is why you have D4PG and D3PG. So the difference between these two is whether they use the distributional side or not. We don't care about the distributional, so let's put a big X on the distributional word. Although if you want the details, you can find them here in the paper, and you find also the code available here. And here we have a very simple architecture again, which is similar to the one of IMPALA, except that in this case we use an off policy. We use an off policy algorithm, and we use a replay buffer. So here again we have each agent which has a version of the actor and collects data. These data are then stored in the replay buffer, from which the learner samples batches of data. And actually, this is a prioritized replay buffer. So this is why we have this step where we compute priority queue, and then the learner returns the updated actor to the to each actor. And note that in DDPG we have a deterministic agent, right? So this is one of the things that it's probably important to say. And the fact that the update between the different rollout workers, among the different rollout workers, that can be can happen at different time, also improves the exploration compared to standard DDPG. Okay, then starting off from IMPALA, we have seen that there is this V trace where basically we are computing the targets for the V function in a way that is using important sampling weights. Seed reinforcement learning is the basically one of the latest algorithms that has been introduced for distributed reinforcement learning. And in this case, we are combining IMPALA with R2D2, which is an algorithm that I will describe very quickly after this slide. But to characterize Seed RL, we are dealing with an off policy algorithm that is using like D3PG and a replay buffer, and specifically it's using a recurrent distributed replay, which is then combined with R2D2, which is a version of Q-learning, which I will be describing soon. And anyway, if you compare IMPALA against Seed RL, you notice that on the same GPU, on the same accelerator, with less actor CPUs, we have much less actor CPUs, we have an amount of frames per second which is more than half the ones that IMPALA collects, meaning that even if you have less actors, this algorithm is working in a more efficient way. And as you notice from this figure, one characteristic of CDRL is the fact that not only training is centralized, but also inference is centralized. And this is the scenario that we described before, where each actor sends the observations to the learner batches them, then it returns the actions in batch, which are then delivered to the correct actor. And yeah, so if you look at the returns here, notice that the returns collected by CDRL are much higher with a reduced amount of hours of training compared to IMPALA. Now, you said we use R2D2, we have no idea what that is. And this is the description of it. As I said, it uses experience replay. And this experience replay, however, is a recurrent experience replay where we store trajectories instead of transitions. So we store trajectories of fixed length. In this case, they select 80. So there are 80 sequences of state, actions, and rewards. And you don't have next state because the next state, you can collect that just directly from the next frame in the same trajectory. So you have this information that is stored in a replay buffer. And this is done in order to deal with partial observability, because in games, for example, like Atari games, you only use the image, which is not returning the full information about the state. It's only partial observable, so that's why you want to deal with that. In previous papers, this was solved by stacking together the last 3 or 4 frames of the agent, of the environment returned by the environment as a single state. In this case, they instead avoid to do that, but they store the full trajectory in it, and they treat this as a partially observable problem. But then if you train with trajectories, then you use something like a recurrent neural network, which in its own has some issues, specifically the 0 state, how to initialize basically the state in the recurrent neural network. And they come up with 2 possible solutions. One is the fact that you store in the replay itself the recurrent state, and then you use that to initialize the network at training time, right? Because when you do the rollout, each individual actor will have some state, some hidden state, and that makes a difference and is part of what makes the recurrent neural network work on this kind of problem. So you need to be able to use that in some way. And one solution that I propose is we store directly this information inside the replay buffer. So they will have the hidden state, the observation as part of the state, and then the action and whatever, and the reward. The alternative approach is that of using a burn-in, where you use a portion of the data that is stored in the replay buffer to unroll the network and start computing the hidden state. And then when you roll a bit of it, you start the training from the hidden state that you computed, and you basically use a bunch of the transitions that are part of this trajectory in order to initialize your recurrent neural network. The most efficient approach that they found is using a combination of these 2 things, which makes things work quite well. And then the training happens with this ApeX schema, which we'll look at in 1 second, which is here, where ApeX is nothing else than a distributed prioritized experience replay. So the training happens in such a way that you have a prioritized experience replay. For new samples, you compute the priority. instead of, if you remember when we talked about the prioritized experience replay, we said for new samples, we set the priority of these samples to their maximum priority level. In this case, they don't do that. They compute the priorities for each sample, also the new ones, based on the DDRs we saw last time. And yeah, so this is the schema that they follow for training, where there is this learner that receives experiences from the replay buffer, updates the priorities in the replay buffer for the prioritized experience replay, and then returns the parameters of the policy to the each individual actor. And yeah, then they collect the experience, they store that in the replay buffer. And they also calculate the priority when they collect of the new samples. That's why you have this step of initial priorities. Okay, so this is more or less how it works. When I mean, there is nothing exceptional in this Apex schema, except that they use prioritized experience replay with priorities being computed from each actor when we receive new samples. Okay, yeah. One last point that I wanted to make is that similar to when I introduced reverb, here I want to describe very quickly a framework for doing distributed reinforcement learning, which actually makes use of reverb. And this is called Acme. So you will find the code available here. This has been released by DeepMind. Again, they're releasing most of these things. And this Acme is nothing else than a reinforcement learning interface that connects an actor to an environment. And if you do this, it's very easy to, if you use Acme, it's very easy to implement a multi-actor algorithm and scale up the number of actors to 2, 8, 16 in a truly distributed or locally distributed fashion. Yeah, so the same way you implement the main actor, they basically scale it up for each. The framework scales that up for several distributed actors without you having to do a lot of work. You just need to specify the number of actors that you want, and it's used the experience replay. Then it's up to you how to set up the experience replay. As I said, it makes use of reverb. Besides, you know, reverb implements different ways of doing experience replay, so you can do prioritized, uniform, whatever you want. And yeah, that's actually it for today. It was a short class, as I mentioned, because the topic to cover is quite easy. I think there is of course time for you to ask questions if you have regarding the the topic first, and then we'll discuss about the exam stuff. If you have questions regarding the topic. Okay.
So
then
I have a quick question. It was just not very clear to me.
The streaming.